Okay, so we are going to look at graphing rational functions. Before we start though, I want to kind of look at the different attributes that you're going to be asked about and kind of take some notes on those so you can identify them as you go through the sheet that you're going to work on. So the form of a rational function is f of x is equal to p of x over q of x. P of x and q of x are polynomials. And it's really important that q of x, because it's in the denominator, is not equal to 0. So every single time we're going to follow the same few steps when we're doing this. So the first thing we're going to do is to simplify that fraction if we can, using the things that we've been using like GCF and then factoring in general. So we're going to simplify that fraction. If possible, sometimes it's not, but it's always good to check because it does make your life a lot easier if something does kind of cancel out. The next thing we're going to do are x-intercepts, or where the graph crosses the x-axis, is where the numerator is equal to 0. The next two things we're going to talk about are vertical and horizontal asymptotes. So for those of us that don't know, asymptotes are the line that the curve approaches, but it never touches. So they're going to be kind of these barriers on our graph that the graph's not going to be able to go through. So vertical asymptotes. Now this is where the denominator equals 0. Still in the frame? Good. Okay. And then the horizontal asymptotes have different qualities depending on the actual given function. So we'll look at a couple of different cases when, or if and when we have a horizontal asymptote. So if the degree of p is greater than the degree of q, there is no horizontal asymptote. So remember, the degree is the exponent of that leading term in the polynomial. If the degree of p is less than the degree of q, our asymptote is going to be the x-axis. If we're giving it in an equation, it's where y equals 0. The last case is where the degree of the numerator and the denominator are equal. And when that happens, you're going to use the leading coefficient of p divided by the leading coefficient of q. Okay, there's one more thing that this is pretty much new for everybody, I believe, is talking about holes in a function. So it's where the function is not continuous, so there's just a little bit of a break. So the last thing we have to do before we graph this thing is to identify any holes in the function. And again, that thing, a hole, is any point x comma y on the graph in which there is a break. Now, holes occur when p of x and q of x have a common factor, which is why it's so important to factor those things when you're first given the problem. So in order to find the whole, to get the x coordinate, you set the common factor equal to 0. And solve. And then to get the y coordinate, you substitute that x into the simplified function. So after you factor everything and kind of cancel stuff out in the numerator and the denominator, that is where you plug that x back into. So we are going to look at a few examples together. So this is from the worksheet that you have. It's uploaded on Google Classroom for you. So I'm going to look at 1 and 4 with you right now. Okay. So when we're looking at number 1, again, the first thing that I'm doing, so I'm following that little cheat sheet that we just did, is to simplify the fraction. So looking at this numerator, there's a GCF of x, so I'm going to factor that out to get x plus 2. And then in the denominator, I'm going to factor out that -4, and again, to be left with x minus 3. Now, these don't have any common factors, but this would be the time where I would cancel those out if they did. So we're looking at that first, and then I'm going to write out a list of all of the things that the directions are asking me to do. So I need any wholes, the vertical asymptotes, the x-intercepts, the horizontal asymptotes, and the domain. Okay. So we're looking at wholes, and our notes say that so this is when p of x and q of x have a common factor. So because our numerator and our denominator don't share any factors, there are no wholes here. The vertical asymptotes is where the denominator is equal to 0. So I'm taking this and setting it equal to 0 and figuring out where those asymptotes are. So subtracting 12 and dividing by -4 to get x equals 3. So my vertical asymptotes, just one, is that x equals 3. The x-intercept is where the numerator is equal to 0. So I have x and x plus 2 is equal to 0. Because this is in factored form, this times this equals 0, which means that one of these factors also has to be equal to 0, zero product property. So this one's easy, right? That one's simple, and then we're going to subtract 2 to get the other one at -2. So I know that the graph crosses the x-axis at 0 and -2. Horizontal asymptotes. So it says the degree of p. So I'm looking here. The numerator has a greater degree than the denominator. So because the numerator has a greater degree than the denominator, the numerator has a degree of 2, denominator has a degree of 1. So there are no horizontal asymptotes here. As for the domain, truly the only thing that x cannot equal is wherever those vertical asymptotes are and wherever the wholes are. So I don't have a whole here, but I do have a vertical asymptote. So we can say all x such that x does not equal 3 is one way to do this. Sorry, this is getting a little messy. There we go. Okay, so from here, I went in and I used my graphing tool. So I know that some of you have a graphing calculator and then some of you are using Desmos, which are both great options to kind of get you set up here. So I got these values from the table function on my calculator, and Desmos will also do that exact same thing for you. I really just want to get a few values on either side of my asymptote. There's really no right or wrong way to do this, just to get the shape of the function that we are looking for. So again, these values all came from that table. On my calculator. Okay, so my vertical asymptote is at x equals 3. So this is a line that is dotted on our graph. Our graph never approaches it, but it does get really, really close. And then I'm just taking those and graphing here. So 12/11, a little bit more than 1, 2/7, a little bit more than 0, 0, 0, 2, 2, and then I have 4, -6. And so one curve is going like this, and the other is going like that. And I did type this into my graphing calculator and click graph, and there it is. Okay. Let's look at another example up here. So let's look at number 4 together to make sure that we know what's going on. Okay, again, writing down all of the attributes that I'm looking for. So I'm looking for a hole, the vertical asymptotes, x-intercepts, horizontal asymptotes, and the domain. So when I'm looking at this, first thing I want to do is factor, just to see if there's anything in common, to see if I have any holes. So when I'm looking at this, I'm factoring the numerator, adds to +1, multiplies to -2. So I'm going to use x plus 2, x minus 1. Denominator to start, I'm being, excuse me, very careful because I have a -3, a 6, and a 24. All of those are divisible by -3. So let's remove that first, and then kind of go from there. I can factor this denominator further, which is what I'm going to do. So it needs to add to -2 and multiply to -8. So I have x plus 2, x minus 1 in the numerator. And I have a -3. And that trinomial inside the parentheses is going to factor to x minus 4. X plus 2. Notice I do have a common factor here of x plus 2, so I'm going to go ahead and eliminate those, but that does mean I have a hole. So that first thing that I'm going to do, it says, so p of x and q of x have a common factor. To get the x coordinate of the hole, you set the common factor equal to 0. So set this equal to 0 to get the x coordinate of my common factor. So x is equal to -2. And then to get the y coordinate of the common factor, I plug in -2 back into this simplified expression. Okay, so what I have here is -2 minus 1 over -3 times -2 minus 4. So -2 minus -1 gives me a -3. -2 minus 4 gives me a -6, times -3 is a +18. So -3 over 18 simplifies to -1/6. So because this is a hole, the first thing that I'm doing is I'm going to this point and I'm actually going to make a hole. Your graphing calculator, your graphing tool is not going to do that for you. So it's really important that you do that because on your graph it will look continuous. Okay, vertical asymptote is where the denominator equals 0. This is in the simplified expression. So I'm only looking at this part, which does make our life a little bit easier. We already identified that this couldn't be x because of the whole. So we don't have to worry about that anymore. So when I'm looking at this, I'm trying to figure out where this equals 0. That 3 will go, and I'm left with x minus 4 equals 0. So I have a vertical asymptote at x equals 4. The x-intercept, again, is where the numerator equals 0 of my simplified expression, right? I'm gonna come over here, we're still good, okay. I'm gonna come over here so that we can see that. So I have x minus 1 equals 0. So my x-intercept happens at 1. My horizontal asymptote. So here the degree of P is equal to the degree of Q. My leading coefficients are 1 and -3. So that fraction for leading coefficients happens at -1/3. And again, that came from the leading coefficient of P divided by the leading coefficient of Q. Lastly, the domain comes from everything except for the wholes and the vertical asymptotes. So it's all x values except that x cannot equal -2 and 4. Okay, graph time. So we are doing our vertical asymptote at x equals 4. And then our horizontal asymptote at -1/3. I know these graphs are small, but again, you've identified it here. So as long as it's sketched generally correctly, we should be okay. And again, these table values that I'm about to get came from the table on my graphing calculator. And I want to just get a clear-cut picture of where these curves are happening on either side of this vertical asymptote. So I'm choosing values -3, -2, -1, 0, and then 1, 2, and then I'm skipping ahead to get on the other side of that asymptote to 5, 6, 7. So when I plug in -3, I get -4/21. -2, I get an error message. I want that, right? Because I already identified that -2 was a whole. So the calculator does recognize it for you in the table, but it will not recognize it for you on the actual graph. Okay? And then -1 is at -2/15. 0 is at -1/12. 1 is at 0, which is what we wanted because the x-intercept should be at 1. 2 is at 1/6. 5 is at -4/3. 6 is at -5/6. And 7 is at -2/3. Okay, so when we are graphing these things, -3 and 4/21. 2 is an error, 1, 0, 2 is at 1/6. So this thing is gradually increasing. We're making sure that we're not drawing our graph through that hole and then going from there. 5 is at -4/3. So we should be a little bit more than 1. 5/6 and 2/3. So this curve is going here. And again, all these curves should be approaching these asymptotes, but never touching them. And I know that these graphs are small, but we can do that as closely as we can. And we're making sure that our table's there and all of our attributes are identified so that we can do this a little bit easier.